Hello, welcome to this Python tutorial. And what are we in? We're in video 4 using the Ursina Engine to build a 3D solar system. That's what we're up to. Right, so let's just run it. So this is the exact same code, hopefully, as where I left things in the third video. And I think we got our polar coordinates working. We've got obviously a dark background. We've applied just a single moon texture to all of our planets, and we've got them rotating, I think, at the same speed, something like that. And so what we want to do in this video is actually use data about our solar system and apply that to these planets, including the dwarf planet Pluto. I'm not going to leave Pluto out of things. And also, I think at the start, let's do this straight away. At the start, the editor camera that we're using, which I'm now going to call Smithy. Let's call it Smithy. Smithy equals the editor camera. I want to be able to look down at our solar system, directly above the sun. So what we want to do is give our editor camera a name, Smithy, and then we can get hold of the editor camera and then say something like your position on the y-axis. So we need to go really high up because we're going to use data about how distant each planet is from the sun and apply that to our model. We can kind of scale things down, but the relative distances between the planets will be accurate. So we're making an accurate model of the solar system. So we want to go up really far. So let's just put 8,500 and see where that takes us. And then we need to rotate the camera on the x-axis so it looks directly down. So that would be by 90 degrees or a right angle. So Smithy dot, actually I could just put for position dot y. And then Smithy dot rotation underscore x equals 90. So we should be looking straight down. Also, I'm just looking at things here. Our 9 stars in our solar system. What we did originally to position them and things is we moved them down underneath the sun by 32. We don't need to do that, so I'll just remove that. Right, let's just see how things are looking at the moment. Good evening, by the way. Okay, hopefully you can see that as well. That's really good. That's exactly what I wanted. We're just looking down at our solar system. And we can still use the editor camera. So right click, if you remember, or 2 fingers if you're using a trackpad like me. Then you can use WSAD to kind of move around. Although, if you just saw that flying ball, I've forgotten to look up in the documentation what it is, but it's part of the Ursina engine, something to do with the editor camera. It's like the center of your field of view or something to help you orientate yourself. Anyway, sorry, I was saying if I'm pressing down W now, but because I'm 8,500 units away, it doesn't look like I'm moving. So if we want to create some kind of spacecraft to go around our 3D solar system in the future, we're going to have to perhaps create our own kind of third-person character controller or something like that. Right, so next thing I want to do is make those planets noticeable. So in our planet class up here, we're setting all the planets to grey. So if I make them lime, which is a preset color from the Ursina engine, we'll keep the moon texture, kind of generic moon texture. Then we'll be able to see them more easily. Just in case, I don't know if you could see what I could see. So there they go, circling around. Right. And it does look like they're all moving at the same speed. So let's go and get our data. So what we want to do is perhaps when we're making our planet. So here's our little for loop going around 9 times for each planet. And just to remind you, I'm using this temporary object variable, baby, and I'm saying equals planet, so that's instantiating a planet through the class that we wrote, which gives us an Ursina entity, so a 3D object which has a model of a sphere. Then we're saying its solar distance is how many times we've iterated around the loop times 80 plus 80 to move it away from the sun. So there we want to be able to say something like data, and it'll be about the distance, and then we can say whichever planet you are, so from 0 to 8 on this loop, pull out the data from the list for each planet and then set that planet's distance to that number. And then we also want to do the same thing for its, what do I call it, orbital velocity. So that's the speed that it's rotating around the sun. So we want to say orbital vel equals, again, data, and we want the velocity, and again we want to just pick out the index on that list for our planet. So that will go from 0, the first index, to 8, the last index, so 9 altogether. And again, we are including the 9th planet, the dwarf planet, which isn't a planet, Pluto. Okay, so those don't exist yet. Data dist and data velocity. So let's go and make those and then go and get our data. I've got it already set up. Yep. Okay, so it makes sense to kind of do it here underneath our list of planets. So data from the real solar system. Oh, what should we call the solar system? I never get around. I reckon I want to name it. I did have an idea between filming. Let's name our real solar system, because I'm ignorant about what the name of the solar system is. Everyone just calls it the solar system. It doesn't have a name. So I want to call it, did Copernicus, I'm sure the fellow who realized that, we're going, the planets are moving around the sun, orbiting around the sun. It's not the sun moving around Earth, and Earth being, what do they call it, the geocentric picture of this interplanetary system. It'd be nice if he had a daughter. Does he have a daughter? So we could name it after Copernicus's daughter, and that would be our system. So let's say her name is Samantha. So it'd be the Samantha system. There we go, that's my idea there. So I'll leave that there. Back to the coding. So we want to say data distance, that's going to be the solar distance, equals, and then, so we're going to make a list, but I'm actually going to hard code in there. I'll go and grab it from the table. The distances from the sun for all of the 9 planets, and then we'll do the same for the orbital velocity. What did I name that down here? Was it just orb vel? Oh, vel. Okay, velocity. Vel equals that. Right. Let's go and see if this works. So here we go. We've got this table. Oh, I'll put this in the code so you can find this table yourself. It's from NASA, and it's like a planetary fact sheet. So I'll put the data here. There you go, the website there. Again, this tutorial Ursina 4 solar system Python code, I'll give you a link to my GitHub folder where you can find all of these Python files in the series so far. Right, so we go back to the code, sorry. Right, let's go. Right, what have we got? We've got we also need the diameter, the size, the scale of each planet. That would be good. So the gas giants, Jupiter and Saturn, will look really big, and then like Mercury really small, and so on. And Mars and Earth, they're about the same, aren't they? Okay, so we need orbital velocity. There's one that we need. I've also noticed in this list, we've got the moon. So we do have to take 1, 2, 3, 4th, the 4th datum out. Right, so orbital velocity. So I'm literally just going to drag Command C, copy those, and into, what was that? That was the orbital velocity, wasn't it? And then Command V to paste. There we go. Oh, there's the moon. It's got an asterisk, so actually I can take that out. Lovely, and then just press return. So I've just chopped the list in half in terms of fitting onto the screen, and then we just need to make sure there's a comma in between our values. I don't think it will matter for these spaces. I think our compiler will deal with that. Right, there we go. And now we need to go and get the distance from the sun. Distance from the sun. And we also need to measure our units. Record our units. So it's kilometers per second. And we've got distance from the sun is measured in 10 to the 6, or a million kilometers. So 46 million kilometers. So it's kind of scaled down for us already. Sorry, that was a perihelion. We need the distance from the sun. So 57, in the same ballpark, right? And again, it's got an asterisk. So for the moon, again, it's the fourth one in, isn't it? There we go. Control C or Command C if you're on a Mac. Data distance. So I'm going to delete the moon. Not the real moon. Don't worry. Just the data, and then return. And again, put in those commas. And I think this is a rather efficient way, rather than having to, like, I don't know, do it some other way. I can't think of anyway. But certainly, so we haven't got to talk about every single like planet in a row and then put these in ourselves. We can just copy and paste them in a list, and that reduces human error and things like that. So I think it's not just lazy; it's also good practice for data entry. Right. So while I'm thinking about it, should we go and get our diameter? I'll call that dia. There we go. So another list. Yeah, it'd be good to see our planets with their relative sizes, scale sizes. There's diameter. Oh, the moon doesn't have an asterisk this time, so I'm going to have to count 1, 2, 3, 4. 1, 2, 3, 4. Okay. Right. How do I get to the beginning of the... There we go. 1, 2, 3, 4. There he is. Now I remember the number as well. 3,475 kilometers that will be. Oh, also notice these values have got commas in. That's bad data practice. They shouldn't have that, because these don't have commas in, so should all be consistent. So NASA has let us down. So let's just go and take out the commas, clean our data. In fact, I'll press return there to break the data in half, so it's not just one long line. Just double check that. No commas, no commas, no commas, no commas. Very good. And now put in commas with their proper function just to separate our values. And one final check is I should have 9 data points, 9 values. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. So that's for our diameters. 1, 2, 3, 4, 5, 6, 7, 8, 9 for our orbital velocity, and now the distance from the sun. 1, 2, 3, 4, 5, 6, 7, 8, 9. Lovely, all good. Finally, what I want to do is just record kind of like the meaning of these numbers, because they don't really mean anything without their units. So the distance from the sun, that was million kilometers, I think. Kilometers 10 to the 6. Shall I just million kilometers? There we go. Velocity, that was kilometers per second, I think. km per second, and then the diameter was kilometers. Let's just double check I've done that right. So diameter is kilometers, distance from the sun is per million kilometers, and then velocity is indeed, orbital velocity is kilometers per second. Lovely. So we've got all of those in there. Right, now let's just double check. When we are instantiating our 9 planets, we're now saying your solar distance is data distance P. So I'll pick out the relevant data point for each planet, and the same for orbital velocity. So we haven't changed their scale, their size. So I need to refer to the entity, remember. Looking at our planet class, their orbital velocity and solar distance, that's not something included in Ursina's entities. That's used in our function, which we coded maybe last video. We used it to change the X position and the Z position of our planets. Okay, but so that means the scale or the size of our 3D object, our planet, our sphere, we need to do that through the entity. So ent.scale equals data, what do I call it, dia, and then pick out the correct index. So the first planet, Mercury, will be index 0, then Venus will be 1, and Earth will finish there, will be 3. Sorry, 2. That's hilarious. Right. I'm kind of itching to have a look at it. So what are we presuming will happen? I'm presuming things will be like way too large and maybe way too distant and certainly too fast. Because I think we were originally, the orbital velocities were set to something like, a hundredth of a unit, 0.01, and these values for velocity are like 47, so they're a lot larger. Right, let's just run the module. I think I saved it. Have some tea to calm me down. So I don't know what's going on. Something's spinning very, very fast, and it's very, very large. Right, so let's use a scalar. That just means we can multiply these values, all of them, by the same thing. So we maintain their structure, their correspondence to the reality out there, or here, because we're actually on one of those planets, aren't we? It's a giant ball in space. It is very strange to think about, and we're on it. And then those other ones are going around as well. So anyway, we want a scalar. So we'll call that scalar, and then we want it for the orbital velocity, or OV, and we'll set that to 0.01 to bring it right down. And let's do similar things for the diameter and distance. Distance I'll keep to 1 at the moment. I'm not sure about that. Okay, so what we do then is when we apply those values in our for loop, when we're instantiating our planets, we just want to multiply the distance by dist. Yeah, the distance by dist. What's it called? Distance. Dist, yeah. I've not called them very good names, like consistent names. So let's just change that. OV di dist. There we go. So we've got, that's orbital velocity, isn't it? And that's di for diameter. Okay. So we save that and just have a look at if we can see anything this time. So it looked like we were zoomed in to a planet. Right. So we can actually see something going on. Very good. Actually, the distance It's not too bad. Not too bad at all, actually. The speed is still much too high. So now we can just play around with these values and we're sound. So orbital velocity, we reduce that by 10. And the scalar distance, let's just double that, so a little further away. Oh no, that was their diameter. So actually, I might want to go a little bit smaller. Some of them are a little large. And then scalar distance, maybe get them a bit further away. So we'll double it. Run the module again. Oh, this is looking about, that's a lovely speed. That's about right. So we've got Mercury, Venus and Earth, yep, about the right size. Oh, Mars is quite small. And then do we have Jupiter, the largest gas giant, and then here's Saturn. We definitely have to get rings around Saturn. But we can't see the others. So again, I can kind of like look around. Oh, can I see them like this? They must be really far away. Maybe if I just like stay here for a bit, you've got to wait for it to like pass. I'm not sure. So we definitely need to create our little, our own kind of like controller so we can like zip out a lot further. Okay, so I'm just thinking we need to change our sun skin. So here's our sun. I'm setting Texie to that. I've put a new texture, 2K texture called 2K sun in the folder. Oh, at the position of the sun. Actually, we don't need to change that from 0. We'll just leave that like that. Let's just see what that looks like now. How long has this video been? About 20 minutes, so I might stop this video in a second. So I actually achieved quite a lot. We've got a scale model, solar system. And there's our sun. Lovely. So we can think about what we might want to do. I think colouring each planet will be good. I quite like just using the moon's... oh no, actually it would be good, obviously, to get each texture for each planet. We could do the rotation of each planet. What's that, polar rotation? I can't remember what it's called. I think Venus rotates the other way around. And I think all the planets go around this way. I don't know, if you're looking, I suppose there is no above the sun, is there? There's no orientation in space, so it doesn't matter. I can set them going anti-clockwise if I like. Oh yes, the sun should be obviously like 1,000,000 times larger than the Earth, that third planet here. We might need to move the planets a little further away from each other. Certainly once we can adapt our camera. Yeah, so we need rings, colours. Yeah, I think next video will be about rings and colours, and maybe it'd be nice to have like an automatic script where we can, according to this table, I think it tells us, yeah, whether it's got a ring. So Jupiter's got rings, didn't realise. Saturn has got rings. Uranus and Neptune. Obviously Saturn's, and I think Uranus's rings are very distinct, whereas for the other planets not so distinct. Anyway, what I was going to talk about was the number of moons. So like Saturn's got 82 moons. So it'd be nice if we just have a function where we can put an 82 into the function and then it spits out that number of moons rotating around each planet. And maybe like a button that we can switch on the moons and switch them off. And it'd kind of be cool if the moons were not just going like around like that, but kind of go using other axes of rotation. Yeah, but there we go. So what have we got? We've got a scale model of the solar system called whatever Copernicus's daughter is called. Hopefully he had a daughter or two. And it's being recorded. Right, thank you very much for this video. Again, in the comments, do leave any suggestions and things. And thank you for your comments so far in this series. I've really enjoyed reading them. Goodbye. I can't remember how to stop my new software. There it is. Goodbye.